I'm incredibly happy to introduce the speaker for the second introductory tutorial today, Ian Murray, who is going to talk about Monte Carlo inference methods. If you were at the deep learning tutorial this morning, you probably heard Jan LeCun say that he's allergic to sampling. So I'm pretty sure he's not in the room right now. Ian is a lecturer at University of Edinburgh, and I met him a while back when he was a PhD student at the Gatsby unit at UCL in London. And my understanding is that Ian was actually meant to be a physicist, I think, until he met David MacKay and took a machine learning course with him, which sort of changed his life. And one interesting thing about Ian that you might not know is that when he's not sampling, he's actually juggling. And he's one of the few people, actually he's probably the only person I know who's able to juggle with 5 clubs. All right, so without any further delay, I'm incredibly happy to introduce Ian.
Thank you very much. Can you hear me at the back? So just as the last few people filter in, I want to set expectations. This is an introductory tutorial, so my aim is to get you to understand about Bayesian inference and how we use Monte Carlo methods to solve these problems, and methods some of you might know about called Gibbs sampling, slice sampling, and how to make these things work. So if you're already the sort of person who's derived probabilistic models and implemented sampling methods for them, you might be better slipping out and going next door to a more advanced tutorial. I'm not going to assume anything right now. So Monte Carlo methods are things that I think everyone in the NIPS community should know about, even if you're not going to use them yourselves, or even if you just use them to quickly sanity check something you're doing, but it doesn't make it into the published paper. So this term Monte Carlo is a bit funny. It refers to just using random numbers to do something on a computer. Some people give it a precise meaning, but people have been using random numbers for a very long time. The term Monte Carlo was introduced when people were developing nuclear weapons as part of the Manhattan Project. There were a lot of physicists who were using random numbers, and this term Monte Carlo sort of evolved at that time. So Nick Metropolis wrote this very nice review about the birth of the Monte Carlo method. And one of the anecdotes I really like from this story referred to this guy, Enrico Fermi. So Fermi was a physicist, and he was doing neutron scattering experiments. And he would come into the lab with predictions of how they were going to come out. And he'd made those predictions by staying up late at night and running simulations. But unlike us now, when we have computers kicking around all over the place, they did have some of the early computers there, but he didn't have one. He had a hand adding machine on his desk, and he was doing Monte Carlo simulations by hand. And it was an incredibly useful thing to do, and gave insight into the physical models he was running. So now we do have incredibly powerful computers just kicking about all over the place, and we can use Monte Carlo methods to get insights into our machine learning systems. So what I want to do in the next couple of hours is to give you some examples of how we get insight into our models by just drawing some random numbers and having a look. How we use those random samples to do actual computations, to do math. And we'll look at some of the methods. So as I said, we're going to look at importance sampling, rejection sampling, and these algorithms called Metropolis hostings, Gibbs, and slice sampling. One of the most important things with any method is how do I actually run it so that I get correct answers. So I'll talk a bit about that at the end. But for the moment, I'm going to have a running example, and I want this seminar to be entirely understandable. So my running example is going to be linear regression. We've got a straight line with a slope and an intercept. So our parameters here are 2 numbers, theta. And if you're Bayesian, you'd put a prior on these things. So you say, there are these 2 numbers. I don't know what they are. You could imagine the blue line corresponds to some slope and some intercept. That's the correct answer, but we're never going to know what that is. So instead, we consider all the possible lines that might be the true model. So we could have this distribution, just for simplicity, a Gaussian. These are the slopes and intercepts I think might be plausible. And we could look at that model by, for every vector of 2 numbers we sample, drawing a line, saying this is the corresponding model. And if you do that, you immediately notice stuff like there's a big bunched up region here near the origin, and maybe you hadn't thought about that when you wrote down the model. Maybe you need to think a bit about how the data will be centered, or maybe we need to reparameterize the model to try and make the position of that bump more flexible. So it can be a good idea just to do a forward simulation, like look at realizations of your model and question whether they make sense. Of course, what we're usually interested in is having data. This is just a model. So the way we'd get data for this model would be we'd see these black lines, they're data points, yn. They're evaluated at our line plus some noise. So if we have data, we can use this prior distribution to come up with a posterior. What do we believe about these two numbers given the data, which is proportional to how well those two numbers explain the data and how plausible a priori they are. So we can't really see what's going on in this graph because that region is really tight. So normally if we get lots of data, hopefully that data is informative and our beliefs will be much tighter and in a smaller region than our prior beliefs. So I'll zoom in on that region. This is exactly the same graph, I've just zoomed in, and you can see the data points. And this posterior distribution, what I've done is I've drawn samples to understand it. So I've drawn 12 samples from the posterior distribution. None of these purple lines are the correct answer. I will never be able to discover that correct answer, the blue line, from a finite amount of data. All I can do is say which models are plausible and which ones aren't. So the 12 samples there are showing 12 examples of the sorts of model that could have generated our data. And you see they surround the correct answer. Near where we've got lots of data, we end up really certain. So we know exactly what's going on there. And as you move away from the data, you get the possible explanations really spreading out what predictions they'd make. So Bayesian inference just automatically does this very clever thing that if you go to a region where you don't have data, you can automatically be less certain, and that's just fallen out of the maths. We didn't have to put that in as a hack. We've got this nonlinear envelope over where the lines are, even though we've got an underlying linear model. So we get an interesting predictive distribution by looking at these samples. I'll just push this example slightly further. There's only so interesting linear regression can be. But what happens if our data aren't linear? So usually in the real world, we're going to get data which is more complicated than our model. So here I've got some data that if we look at it, there's clearly a nonlinear trend. We could ask ourselves, what would happen if we did Bayesian inference with this data set, but using the same linear regression prior that I've already showed you? And this is something I ask my students back home. So I give them a quiz question. I say, we've got this data set, and I'm going to do the same thing I did before. I'm going to draw 12 samples from the posterior and say what possible lines are plausible given this data set. And various things might happen. So for example, is the model going to choose to explain just the left-hand part of the data, or the middle of the data, or the right-hand side of the data? Or maybe all of those things will happen. So maybe if I draw 12 samples, I'll get 4 of each, or roughly 4 of each. Maybe something else will happen. What it's not going to do is come up with a nonlinear prediction because it's a linear model, but maybe there's something else we haven't thought of. So something I do with my class is make people raise hands. There's a lot of you here, and I'm not going to be able to count, so I'll just let you pause and think for a moment. So come up with your answer. And what happens is I can draw my 12 samples from the posterior, and here they are. So there are 12 purple lines, but they're all almost sitting on top of each other. So from these samples, I can see that the posterior distribution is incredibly certain that it knows exactly what the explanation of this data set is. It's clearly wrong. Like, this point here is a 12 sigma outlier. Like, if you just look at the data set and you look at the model, you can tell that it's massively ill-fit. But nothing in the Bayesian computation for computing the posterior notices that. It assumes that your model is correct. So if you have a model which is too simple, it's not able to express the flexibilities in your data set, then you can end up very strongly peaked around the least bad explanation. you don't get this trend line here because that would be a 20 sigma outlier, which is almost infinitely bad. So you're forced to find the least bad situation. So looking at the samples and doing some sort of model checking can be a really important part of a Bayesian procedure. Okay, so looking at samples is something I do all the time. I'm a bit of a nerd and I like sampling, so I just like looking at these things. But really, as a computational audience, we want to know what math can we do after we've drawn these samples. So this equation is what a lot of people mean by Monte Carlo. Some people, if they say the term Monte Carlo, they mean what's on this slide. And it's about integrals. Here I've got an integral over some parameters, weighted by a distribution over those parameters, of some function. And the meaning of this integral is it's just the average value of that function if I were to consider the distribution pi as where the samples come from. And just saying that, it's hard for me not to say, oh, it's the average value you'd get if you just drew a bunch of samples from that distribution pi. So the almost obvious Monte Carlo estimate of this integral is to draw a bunch of samples from the distribution, evaluate the function for each of those samples, maybe 12, and then just take the empirical average of the samples instead of the true average, which is an integral that means you'd have to consider the whole space, every possible setting of the parameters. So Monte Carlo summation is, in some ways, an obvious idea. It's something that people running surveys do all the time. So, for example, imagine I wanted to know the average IQ of attendees at NIPS. Okay? That's a big sum. It's nearly an integral. And the exact answer would be, I would round up all 4,000 of you, administer an IQ test to every single one, and take the average value. And I could clearly get a pretty good idea if I did the much cheaper operation of grabbing 12 of you at random, giving 12 of you IQ tests, and taking an average of those 12 numbers. And that would tell me sort of what percentile roughly you were in. I'd have to be a bit careful about how I gather those samples. I probably don't want to just take the 12 people on the front row down here. That might not be a fair sample of the distribution. I'd have the keeners. So as with the rest of this talk, we're going to have to be a bit careful about how we gather those samples. Monte Carlo's got some nice properties. It's naturally unbiased. So each of these function values that I take, by definition, their average value is this integral. So every single term in this Monte Carlo sum is an unbiased estimate of the integral I want. And if I average unbiased quantities, then my estimator is still unbiased. But as I average more and more quantities, the error bar, or the variance of my estimator, falls down. So the variance falls inversely proportional to the number of samples I draw. If I want a more accurate answer, I just survey more people or gather more samples. But it falls pretty slowly. If I wasn't happy with the variance of my estimator and I wanted an error bar that was 10 times smaller, then I need to gather 100 times more samples, because an error bar is a standard deviation. It's a square root of a variance. So Monte Carlo is not very good for getting really accurate answers to like 6 significant figures, but it's really good for getting a quick idea of things. How does this apply to statistics? So these integrals come up a lot in machine learning algorithms. If you look at the Boltzmann machine learning rule or the EM algorithm for interesting models, you need to compute integrals of this form. And integrals of this form also pop up in Bayesian statistics. So in our linear regression example, here is why we need to do integrals. I've got a data set, but what's the good in having data unless I can do something with it, like make a prediction? So what I want to do is make a prediction at this location, x star, and say, where would the next label appear along this dotted line? So what do I believe about the test label y star at this location? And the correct Bayesian answer to that question is an integral. It doesn't involve fitting one line and then assuming we know what's going on. It says, you know how to make a prediction if you assume what's going on. If you assume the slope and intercept, we know how to make predictions. But we don't know that slope and intercept. You should consider all possibilities weighted by how plausible they are. So that's an integral. and we can approximate it with a sum. So instead of summing over all possible settings of the slope and intercept, we can get plausible examples which we can sample. So here are our 12 plausible examples again. I don't know if any of these purple lines are correct. None of them will be exactly correct, but they're all reasonable. And if I assume temporarily that one of them is correct, I know how to make predictions. So if I assume this top line is correct, there's a gray bell curve, which is the prediction of where a label would appear noisily around that line. And I get a different prediction for each of my lines. And the correct way to make predictions is to average those predictions. So if I average each of the predictions from each of my plausible models, I get the green curve, and that gives me a very reasonable description of where that test location could appear. And it's much broader than the beliefs I'd have if I just fitted one line. I could fit a line, I could regularize, I could be very careful about how I fit my line. But fundamentally, if I assume that I know what the line is, I'll end up being too certain. Some of you who are familiar with all this stuff will know that this predictive distribution should be a Gaussian distribution. If I have a linear model with Gaussian noise, everything is Gaussian. And there's clearly a weird bump here, and that's because I've only drawn 12 samples. So if you draw a small number of samples, you get a really good ballpark idea of what's going to happen, but the details are a bit shaky. And the joy with Monte Carlo methods is that you don't have to go away and derive anything new. You just throw more computer time at it if you want a more accurate answer. So here's exactly the same slide, but with 100 samples. And my predictive distribution is now nearly on top of the black line, which is the predictive distribution that I analytically derived. So with incredibly simple code that just draws some samples and takes an average, I get like the correct Bayesian prediction without having to derive loads of stuff. Those curves are never going to like exactly overlap. If I wanted to make this slide have the green and black lines on top of each other so that you couldn't tell the difference, I'd need something like 100,000 samples. And to make them agree to several significant figures, I'd need more. So if you want to know something to 6 significant figures, you don't want a vanilla Monte Carlo method. But I don't really care about the position of that curve to 6 significant figures because it's a bit sensitive to the precise modeling assumptions I've made, and I don't really believe the 5th significant figure of any number anyway. So in this figure, I admitted that I could actually make this prediction exactly. So I drew this black line, which is the true answer to this integral. So what's the point in doing this sampling stuff if you can do things analytically? And the answer is there isn't one. You should do the math. But this model, linear regression, or generalizations of it like Gaussian processes, are about the only Bayesian models for which we can do the math analytically. As soon as you make the model at all more complicated, you suddenly don't know how to do this integral to make predictions. So examples of more interesting. Even if we're still assuming that labels come around some function with some noise, if our function is a nonlinear function of our parameters, for example, a neural network, I hear they're popular here these days, or if you had a more interesting noise process, or if you had hierarchical beliefs, like you thought there was some structure to the weights and you wanted to infer hyperparameters, all of these things would suddenly make the model hard to deal with analytically. As another example, which I'll come back to later, you might want to make the model robust. So rather than assuming your data comes from some simple form, you might want to explain away some data points as outliers. So one way to do that is to have a binary variable. Zn can be 0 or 1. If it's 1, then we assume the label is an outlier. It's drawn from some junk distribution that has nothing to do with the input location x. And our model could have some probability that an indicator is 1. So epsilon could be 0.1, saying 10% of your data points are going to be outliers. So if we wanted to infer that quantity epsilon and deal with all of these extra quantities we don't know, z, we don't have an analytic way of doing all of that, and we'll need some sort of computational method that's practical. So if you build one of these models, you have to make a series of choices. You have to say, what hyperparameter would I have? What weights will I have given that hyperparameter? What noise processes do I have? And then, given all of those parameters, how would I generate all of the data given those parameters? So what you can do is imagine trying to build a simulation of this model. If I wanted to draw some synthetic data and ask, have I accidentally made some silly modeling assumption, you'd need to write down all of these probabilities, and you'd sample from them in turn. And a lot of people in this community would represent that equation as a graphical model. In the tutorial next door, they'd represent it as a computer program where you would have a series of steps saying where each variable comes from in code. So for this tutorial, what I'm going to do is not have this splurge of maths on every slide. I'm going to try and keep the notation simple. So I'm going to talk about things that work fairly generally. So they do work for models with a huge bag of unknown things. But I'm just going to call all of those unknowns, the parameters and the latent variables, theta. So theta is going to be everything that we don't know, everything that we would have to generate before generating our data, but that we don't observe in the real world. And everything that we do observe, that could be an input location and a label, but it could be a structured object like a graph, that's going to be D. So what we're going to be doing is looking at methods that will let us look at what's a plausible explanation of our data? What do we believe about this whole bag of unknowns in our model, given the data that we have observed? That comes from Bayes' rule. And all we need to know, usually, is that it's proportional to this probability of everything. So the probability of everything is this spray of maths I wrote down on the previous slide. It's just the product of all of the probabilities that you would compute while sampling these objects if you were doing a forward simulation and having a look at what happens. So if we can sample from this distribution, we can then make predictions. And there's another piece of maths we can do, which we might do if we're interested in, say, just one of these parameters. So say I had scientific interest in how corrupted my data set was. For some QA report, I had to say how much of my data I thought was corrupted. I might want to estimate that number, and I might care about how certain my beliefs in that number are. So then I'm not really interested in an explanation of all my data. I just want to know, what do I believe about this one parameter given my data? And that's another integral. So this integral is what people call marginalization. And for a lot of people in the NIPS community, this equation is called approximate inference. So a lot of people, when they say, I work on approximate inference, or I have an approximate inference algorithm, a lot of the time what they mean is, I've got a method that will compute what to believe about something given data in the context of a larger model that talks about lots of other stuff you don't care about. So algorithms like expectation propagation and variational methods and message passing are really good at this approximate inference problem, coming up with marginal beliefs. And to be honest, I usually forget that marginalization is even a computation when I'm doing sampling. Because when you're doing Monte Carlo, there's no integral to do or no complicated maths to do. What you do is you sample everything. You sample complete explanations of where your data came from, and then you just throw away the bits you don't want. So if you sample entire vectors theta, and you throw away all but the ith element, then by construction, those things automatically come from the right distribution. So I could sample explanations of my data set, and then I could just look at the values of epsilon in those samples and plot a histogram of them, and that would be my beliefs about that noise parameter. So sampling, in some sense, solves a harder problem than a lot of these other algorithms you may have heard about. Coming up with a joint explanation of everything that's behind your data might be more than you need, and that might be part of the reason that it doesn't work as well as some of the other approximate inference methods. On the other hand, it's a much more powerful tool. It gives you whole coherent explanations of what could have gone on behind your data set, and that can be hard to pull out of an algorithm that only gives you marginals. So those are the computations we want to do. We want to solve integrals. The marginalization one is trivial, the prediction one is easy. And we can do that if we can draw samples from all of these distributions. And you might have noticed that I didn't actually tell you how I did that. So I had these plots, and I had samples, but I just sort of said, trust me, I've done this correctly. So what we're going to do is look at the algorithms to actually generate these samples. And I'm going to start off with sampling synthetic things from a model. So this forward simulation, where we just want to look at what our model would do and see whether we believe it. How do we implement those? Well, the answer is we don't. So if you want to sample from any distribution that has a name, like a gamma distribution or a beta distribution or a Gaussian, then that's something that I've never, well, no, I have implemented it because I'm a nerd, but there's no reason to implement those things. There are library routines in MATLAB and R and the GSL that you can just call. So for every sequence in your simulation, you can just call standard library routines and generate synthetic parameters and then data. And this book, which is free online, explains how some of those library routines work. And I'm going to have to explain how a couple of them work because we're going to need to understand those to do more interesting inference problems. So in all of this explanation, I'm going to use the following notation. There's going to be a distribution we're interested in called pi. All of our unknowns are going to be theta, and we're going to want to sample from that. And it might be a simple distribution, like a gamma distribution, or it might be a posterior distribution, a distribution over what models are plausible. And in those interesting cases, we normally can't evaluate pi for a particular setting of the parameters. Usually, we can just evaluate some unnormalized version of it that I'm going to call pi star. So for Bayesian inference, pi star would just be our probability of everything, which we can usually evaluate. And this normalization constant, the probability of data, or the likelihood of our model, for the purposes of this afternoon, we don't know how to compute. So we want sampling algorithms that all that we're able to do is, for some settings of our model, evaluate some relative score that says how good they are. And then we want to be able to sample given that. Okay. So the first standard distribution that's really easy to sample from is an arbitrary discrete distribution. So this is something that I do write code for because it's usually one line. If I have here a discrete distribution over 3 values, theta can be A, B, or C, then you create a stick of length equal to the probability of that value. So the probability of getting a C here is 0.2, so I've got a stick of length 0.2. You lay those sticks side by side, and because probabilities add up to 1, your stick is of length 1. You draw a random number between 0 and 1, here 0.4, and that tells you to sample the value B. So any discrete distribution we know how to sample from, there's no big problem, unless maybe there's a huge number of values on this stick. And I'm going to tweet a link to the slides after the talk, so you can get these references in the slides. It turns out this algorithm isn't the best way of sampling from a discrete distribution. It's what I'd use if I had 2 or 3 values. But if you have a large number of values, there are cleverer things you can do. And I'll just leave it at that. Continuous distributions are harder. So there is a generalization of this laying things out on a stick idea. If I want to sample from some continuous distribution pi, I can transform a uniform random variate. So if I draw a random number A between 0 and 1, there is some maths I can do that will transform that value into a sample. And the maths involves doing the continuous generalization of laying stuff out on a stick like this. You have lots of little elements that you lay out on the stick, and you have to solve integrals and invert them to work out where on the stick your sample has landed. So you can do that maths for some distributions, but for an interesting model, a posterior over even one quantity, you often can't do those integrals. There's a nice geometric interpretation of how sampling works, though, which is if I wanted to sample from some arbitrary distribution that doesn't have to be normalized, what I can do is throw darts at the area underneath that curve. So here I've drawn 4 samples fairly uniformly at random from the area underneath this curve. And if you do that and read off the value that they land, that gives you samples of theta. The probability of landing in a small region around here is proportional to the height of the curve, so it's doing the right thing. Things are sampled in proportion to their probability. If you wanted to implement this, the area to the left of one of these samples is uniformly distributed. So we could call that area A, and that's precisely what this maths up here is doing. So this is a nice picture, but it doesn't necessarily tell you how to implement the algorithm, how to draw these samples. An algorithm that does let you draw samples under the curve is called rejection sampling. So rejection sampling assumes that you have a set of library routines that can sample from some convenient distribution. So for example, a Gaussian. And you use that distribution to upper bound the distribution you're interested in. So here I've multiplied the nice distribution Q by a constant K so that the green curve is entirely above the blue curve. What I can then do is sample points uniformly underneath the green curve because I know how to do that. I know how to sample points from the green curve and then select random heights underneath it. Some of those samples will land above the blue curve, and I'm not interested in that region, so I just throw them away. And as soon as I get a point underneath the blue curve, I can treat that as a sample. I haven't unfairly biased myself towards any location underneath the blue curve, and so I'm sampling uniformly underneath it, and then I can read the location off, and that's an exact sample. So rejection sampling is widely used and may have been used by almost every person in this room without thinking about it. So if you open a MATLAB session and you type rand_n to get a Gaussian random number, somewhat surprisingly, the fastest way to generate a sample from a Gaussian distribution is rejection sampling. They have an incredibly cleverly derived tight bound, which is designed to work well with binary arithmetic. That upper bounds the Gaussian curve, and it accepts samples like 99% of the time, and so is incredibly fast to sample from. If you've got a complicated posterior distribution, it might be harder to come up with a good upper bound. And if you've got more than one parameter and you want to do the multivariate version of this figure, things get very difficult. It can be hard to provably upper bound the curve at all. And if you can, you might want to be clever and come up with the optimal constant that will bound it as tightly as possible. And even then, you might have a large area where you reject a lot of computation. So rejection sampling is one of the main methods used in library routines to sample from standard distributions, but it's basically not used very much in Bayesian computation because it's pretty, or at least not by itself, because it's very hard to get working. So we need some other ideas. And one of the ideas that's still very simple to implement is to not throw away all this computation we're doing. So here I've generated 3 samples and done a load of computation. I evaluated my distribution pi star to work out that I need to reject them, and I just threw all that computation away. And there are methods that think, well, maybe you don't need to do all this stuff. What if you don't need an exact sample? You're solving integrals. Maybe we can solve those integrals more directly. So that's the trick of importance sampling. If what we're mainly interested in doing is making a prediction or doing some other integral we need for machine learning, then we can rewrite that integral by multiplying by the distribution that we know how to sample from and dividing by it. So here I've just multiplied by 1. I haven't changed anything. As long as I didn't divide by 0 here, that would be bad. So I have to pick a convenient distribution Q, which isn't 0 anywhere that my distribution is non-zero. And now, as I've colored in blue, this is just an expectation under Q. So I've rewritten my integral so that it naturally looks like an average under, say, a Gaussian distribution or a Cauchy distribution or something I know how to sample from. So I can now do simple Monte Carlo. I can draw samples from that distribution and average what's left. This is called importance sampling because this quantity, pi over q, is called an importance weight. It's saying some of those samples that you're sampling a lot because q is high, they're not as important as you think they are. But some of them where the distribution has a really high value, you need to upweight those. That's an important region where you need to pay attention to the function values there. So This is easy to implement. You just need a standard library routine and to be able to evaluate this thing. Oh, except we don't know how to evaluate that thing. So if our target distribution comes from Bayes' rule, we often don't know how to evaluate this quantity here. We only know that up to a normalization. So if we can evaluate that, this thing is unbiased and it's great. But if we can't, we need a different version of the algorithm. So there's another version of importance sampling where you still draw parameters. So this is like the slope and intercept of our line or the weights of our neural network from a distribution. But we compute unnormalized importance weights. So we evaluate the function we do know how to compute, the probability of everything, and compute these weights. And then we make them add up to 1. So we create normalized importance weights that add up to 1. So now, for every setting of the parameters I've sampled, I've got a positive number, and those numbers add up to 1. So these quantities are like a discrete probability distribution, or they are a discrete probability distribution. It's a vector of numbers that add up to 1. And what importance sampling does is it replaces this integral, which is an average under pi, with an average under this distribution R. And if we draw a lot of samples, this distribution R, which is a spiky distribution, it's a discrete distribution, will eventually have the same effect as pi for most reasonable functions. So as we draw many, many samples, we'll get a consistent estimator, and we can approximate any integral by sampling from a distribution that's convenient to sample from. So the downside with any estimator is that maybe it doesn't converge very quickly, or it's very noisy for a small number of samples. So if this was just some general integral, you could compute its variance and do a load of maths. But as we're interested in doing Bayesian inference, I'll just show you pictures to see what goes wrong with importance sampling. So here's our linear regression example. And we need a convenient distribution to sample from. If we pretend we don't know how to sample from the posterior directly, we need some other distribution to sample from. And here I've drawn 60 samples from the prior, because that's a Gaussian distribution I have kicking around, and it's meant to be reasonable values of the line. And what importance sampling corresponds to here is precisely assuming that the true line is one of those 60 gray lines. We don't know which one, but we're going to assume it's one of them. So what I'm going to do is I'm going to compute the importance weight for each of those 60 lines and recolor them with intensity proportional to their probability. So then we're going to see what the posterior distribution looks like. And it looks like that. So 59 of the lines are so faint you probably can't see them. And one of the lines has probability 0.9999. So given this overly simple model that our regression surface was one of this restricted set, we end up rammed into believing that the least worst explanation is the correct one. And that's something we've seen before. And we're going to then make wild extrapolations, like believing we know exactly what's going on over here, even though that's not justified. So importance sampling breaks down if we don't draw enough samples to be able to get a reasonable renormalized distribution. So I can just draw more samples and run the same code, but with more samples. If I draw 10,000 samples from the prior and I recolor them, I get this figure, which is much more reasonable. So I have a spray of lines. The darker purple ones are the more probable ones, but the fainter ones you can see might also happen. And they're spread around the true answer. So now I get reasonable beliefs that I could use to make predictions. And again, I see that I'm not very certain far away from the data. So it does the right thing. So incredibly short code. I just drew some samples from the prior, which meant sampling slopes and intercepts from a Gaussian distribution, computing how probable the data was under each of those possible explanations, and then coloring the lines. We want more interesting models than this one. If we have a nonlinear data set, I might need a more complicated model. So here are 12 samples in gray from the prior of a more interesting model. So these are curves with roughly the right sort of frequency or length scale and amplitude to match this data set. It's a reasonable prior that I've constructed by hand. And in purple, I've drawn 12 samples from the posterior. So I did that exactly just to show you that this is a sensible model that will make precise predictions near the data and be uncertain away from the data. So what happens if we do importance sampling here? If I draw 10,000 samples from the prior, so instead of drawing 12 gray curves, I draw 10,000, and I recolor them. Here is my posterior distribution over what I believe generated the data. 9,999 of the explanations were terrible, and the 10,000th was also terrible, but not as terrible as all the others. So I end up really certain that this is precisely what's going on, even though it's obviously wrong. So I could draw more samples. That's what happens after 100,000. That's what happens after 1 million. So if I draw 1 million samples, that's still pretty bad, that one, and the other 999,999 were worse. Importance sampling simply, at least this vanilla version, simply doesn't scale to interesting problems. If you have more than a few parameters, or if your data is informative so that it will rule out a lot of models that you sample from some reference distribution, then you simply can't compute predictive distributions using this method. So what we need to do is go back to the 1940s and 50s and see what the physicists did when they wanted to sample from complicated distributions. So for the next sort of 50 minutes or so, I'm going to explain some of these methods which are based on Markov chains. And it dates back to this paper from 1953. I just had to put up this paper because the opening of it is so awesome, and I really wish I could write a paper like this one day. The purpose of this paper is to describe a general method suitable for fast computing machines of calculating the properties of any substance. That's pretty cool, especially as our fast computing machines are a lot faster than their ones. So we should be able to do a lot with this method, including computing the properties of almost any model. So a lot of what we do is still very much based on this paper. You've probably heard of the Metropolis algorithm, and you will do shortly. So Nicholas Metropolis is the first author of this paper. You'll notice the authors are in alphabetical order, as is common in some fields. Some of the other authors you might have heard of. So Edward Teller is known to some as the father of the H-bomb. And he apparently was the one who had this idea of using Markov chains to explore models. And he had an idea of using some convenient system we could simulate on a computer to explore models. So there's a paper I've linked to at the bottom by Marshall Rosenblatt that explained what these authors had to do with this paper. And you can read the paper for yourself if you're interested in the history. But something I thought was interesting was that Nick Metropolis apparently provided the computer systems for this work. And that shouldn't be knocked. Running a computer system in the 1940s and 50s was a serious task. But apparently he had nothing at all specifically to do with this paper. He didn't come up with the algorithm. He didn't run any of the experiments. He didn't write the paper. Nothing. A bunch of other people did have something to do with the paper. For example, Ariana Rosenblatt apparently wrote all of the code, and she ran all of the experiments. OK, so what was the idea in this paper? The idea was to use Markov chains. And a Markov chain is just a model where if you have a sequence of parameter settings, then the next parameter setting in that sequence is drawn from some distribution. And that distribution only depends on the previous setting of the chain. So an example that you're probably familiar with is if our transition probabilities are a Gaussian centered around the current state, then we'll get a figure like the one on the right. We have this slow diffusion, which doesn't depend on where we've come from, but will slowly drift away from where we started. Over time, this Markov chain would be divergent. It would wander off to infinity. But it does so quite slowly. So if we take s steps, then the distance that we travel scales like the square root of s. So that's one thing a Markov chain can do. Another thing a Markov chain can do is that it can fall into some hole and never come back. So you can get absorbing states. Another thing a Markov chain can do is form some sort of cycle. So there might be a set of states that it just keeps hopping around, or there could be a set of regions that it hops around but never goes to other regions, and after a certain number of steps, you always know roughly where it's going to be. So none of these types of Markov chains are very good for exploring models. What we're wanting are Markov chains that will explore parameters that might have generated our data. And if a Markov chain doesn't do one of these three things, there isn't much else it can do except fall into an equilibrium distribution. So these chains that form equilibrium, if we start them somewhere, they'll fall into some region, but rather than disappearing down a hole or forming into some deterministic cycle, they'll hang around that region in a random way. And after a very large number of steps, the distribution over where they end up will tend to some fixed equilibrium distribution. And I've called the equilibrium distribution here pi because what we're going to do is set pi to be the distribution we want it to be. So the sort of math exercise I'd have had at university on Markov chains would be, here's a definition of a Markov chain, derive its equilibrium distribution. But what we're going to do is say, we know what equilibrium distribution we want. We want to explore the plausible parameters for this model. Please give me a Markov chain that will have that equilibrium distribution so I can simulate it. So that's what we're going to do. I need to cover a little bit of theory, not very much theory. One thing is this technical term ergodic, which is really annoying because no two papers seem to mean exactly the same thing whenever they use it. But one definition of ergodic is that this equilibrium distribution that it forms is the same no matter where you start. So if I'd initialized the Markov chain somewhere else and followed it, it wouldn't have wandered off and reached some other equilibrium distribution. It would have fallen into the same place. And it's pretty easy to make Markov chains ergodic. So at least for discrete spaces, if I discretize this finally, the maths is very easy. And it's very short to show that a Markov chain is ergodic if the state space is connected. If in a finite number of steps, like k equals 100 steps, it's possible to get from any place, any parameter setting to any other parameter setting, then it's not possible for either of these bad things on the bottom to happen. You don't get stuck in an island or a cycle or fall down a hole because you can always get to everywhere in the distribution. So we're going to be interested in ergodic Markov chains. And then there's only really one equation that we need to satisfy for using Markov chains to do inference for this idea called Markov chain Monte Carlo. And that's to understand this one equation on the slide, which is called the invariant condition or the stationary condition. And it's a basic self-consistency property that Markov chains have to satisfy. So we're wanting Markov chains that reach equilibrium over time so that the distribution over where you end up is some distribution pi. So if you ran the chain for a long time and you sample the state from pi, if you then took just one more step to a new place theta prime, you could do this integral to work out the distribution over where you end up. Where do I end up if I draw a sample from my chain and then take one more step? And what we want is that distribution to be pi. We want it so that if we've reached equilibrium, we stay in equilibrium. So our task is to construct Markov chains that have this self-consistency condition and that are ergodic, and then we can simulate these Markov chains and they will draw samples from our distribution for us. And satisfying these conditions turns out to be remarkably easy. So the solution by Metropolis and others was this very simple algorithm. What you do is you use an arbitrary convenient distribution, like a Gaussian, as the basis of the Markov chain. So the basis of the Markov chain could be one of these Gaussian diffusions that by itself would wander off to infinity. And you start simulating that, but you just use that as a proposal. So if we start here, we might propose going to some other place under the Gaussian diffusion. But the algorithm rejects some of the moves and says, no, don't go there, stay where you are. It tries proposing somewhere else. The algorithm says, no, don't go there, stay where you are. But sometimes the algorithm lets you just follow the diffusion. So here we happen to have followed a diffusion that was heading in the right direction after a couple of false starts. We explore the distribution we're interested in, and whenever we make proposals that would wander off outside the support of our distribution, the algorithm rejects some of those steps and kicks us back into the region we're interested in. So it makes these decisions. It says, if you're going to accept, then the next state of the chain is your proposed place. If you reject, then the next state is just where you were already, so you record a duplicate in your sequence of states. And these decisions are made randomly. So there's a probability of accepting the move, and it's some expression we know how to compute. It only needs to involve the unnormalized quantities here that we know how to compute. So within the algorithm, we think about going to some new model explanation. Maybe this slope and intercept would explain our data better. Or maybe this slope and intercept set of binary variables saying which data points are outliers and a bunch of other parameters would explain our data better. We look at whether there's a high probability of the data for those parameters compared to where we are now, and then we decide whether to go there or not. The Hastings version of this algorithm, Hastings is a statistician who wrote a paper in about 1970, generalizes the method so we can have interesting proposals here. So instead of a Gaussian proposal, we might have some cleverer distribution Q. And what this ratio does is stops us from sampling from the wrong distribution in various ways. One thing we might do if we were too clever is make Q behave like an optimizer. So we could optimize and find the best parameters. We could propose going to those. And if we do that a lot, we'll propose going to those parameters with high probability. And this term in the acceptance ratio stops us behaving like an optimizer and says, no, you're proposing those parameters a lot, more often than you should do fairly, and so I'm going to reject that move. So the Metropolis-Hastings algorithm is this, and it gives you a Markov chain that satisfies this stationary condition, and you get to choose the proposal operator here, so you can be creative about how to set that. So what I'm going to do for about 3 minutes is check your understanding, see whether you've been awake. So I have a question for you. This is an example where I'm going to make the state space theta very simple. So theta is going to be a real number between 0 and 10. And in this problem, I'm going to assume that the region between 0 and 1 is interesting for some reason, and the region between 1 and 10 is interesting but different. So there are these distinct regions of my state space that I'm interested in, and I want to be sure that I explore both of them. So I'm going to try and be clever, which is always a bad idea, and I'm going to construct a special proposal distribution Q. And there's maths, but I'll talk you through it. So if you were in the first region, if you're over here, what the maths does is say, it's how far through this region are you, like 90% of the way, and it proposes going to the other region so that you're the same fraction of the way through. So if you're 90% of the way through the first region, you propose going to be 90% of the way through the second region. If you're in the second region, this bit of math says, if you're halfway through the second region, then bounce back to be halfway through the first region. So this is a proposal that, used by itself, would just bounce you back and forth between two particular places on this line. So by itself, it wouldn't be a valid MCMC method. But we can use it anyway within the Metropolis method, and we should be able to get a Markov chain that leaves our stationary distribution invariant. So for example, I should be able to run a Markov chain method and get a sample. That sample might end up here. And then I could use this proposal to propose taking one more step so that the next place the Markov chain visits might be in the other region, so that I might get two samples that tell me about different regions. So if I wanted to run the algorithm, I need to compute this acceptance probability. These proposals are deterministic, so the probability of proposing this particular move is 1. So I've got 1 divided by 1, which cancels, and I could accept with that probability. And what I've just told you is totally wrong. So if you run this algorithm, you don't leave the stationary distribution invariant, and I've done something mathematically evil. So what I want you to do, don't go anywhere because there's too many of you here, talk to your neighbor for like 2-3 minutes and try and understand why does this update not leave the distribution invariant. You could consider the uniform distribution between 0 and 10. You could make pi uniform. Can you see why this algorithm is wrong? And then can you understand what I've done wrong in the math? So chat with your neighbor, introduce yourself for 2 or 3 minutes, and then I'll give you the answer. OK. You're not all there yet, but I'm going to press on. So the main purpose of this exercise is to get you to think about what it means to leave the distribution invariant. So for example, if I sampled uniformly between 0 and 10, 90% of the time I'd end up in this second region, right? So if I applied this update and I accepted with probability 1, then 90% of the time I would sample here and then teleport to the first region. And 10% of the time my initial sample would be in this first region and I'd move it over here. So we can think about what would the distribution look like after one step of this transition. I'd have a big peak that says 90% of my mass is in this first region, and then a long tail saying and 10% of my mass is over this big region. In other words, the distribution over where I end up would be totally non-uniform, even though my target distribution is uniform, and I started out with an exact sample from a uniform distribution. So this algorithm clearly doesn't do the thing a Markov chain Monte Carlo algorithm is meant to do. It doesn't leave even a uniform distribution invariant. And so then the second part of the question is like, well, why not? There's this general algorithm, the Metropolis Hastings algorithm, and I just implemented that. So I thought I was free to pick Q however I want, and now you're telling me I have to be more careful than that. So the problem here is that these numbers, Q, are not 1. I've got a real line, and the proposal here is actually a delta function saying you go precisely here. And the density of a delta function is either 0 or infinity. So really, I did infinity divided by infinity, and they weren't the same infinity. So bad things happened. So if you ever are doing anything with probabilistic modeling, and you have something deterministic, like a delta function or a transformation of variables, you often have to be a bit careful. Most of the maths for Markov chains is really simple if you assume you're in a discrete state space. And usually, even if I have real numbers, I just imagine, would this be OK if I really finally discretized my state space and then ran this algorithm? Because that's what I'm going to do on a computer anyway. I'm going to use discrete binary numbers to represent things. And this is an example of where if you discretize things, it doesn't actually work out. So those of you who know a load of real analysis will hate me for this, but this is the low-tech way of understanding what's going on. I've zoomed into the picture, and I've really finely discretized things. And if I have a parameter on the right-hand side, there are 9 different bins of discretized numbers that would all propose going to the same bin over here. Because when I divided the number by 9, I scrunched down the range. And so the proposal to go from one of those bins to this one has probability 1. It's now discrete. I can talk about probability 1. But what about going back? I've forgotten about where I came from. So you could think of making this choice of which bin to land in arbitrarily. Maybe if you sort of run out of floating point precision, you could just make up the final few significant figures at random. So something you could do is just pick one of these bins at random, which would give you a probability of a 9th here. So you get a factor of 9 in this acceptance ratio. It's not 1. And the reason I'm telling you this is partly to be careful with deterministic transformations, but also because there are algorithms that are really popular in this community where you have to be careful about this issue. So Hamiltonian Monte Carlo or hybrid Monte Carlo was made popular by Radford Neal in the 90s for Bayesian neural networks. And there's a lot of activity around these algorithms at NIPS still now. And these papers contain cryptic sentences that say things like, you need to maintain phase space volume, or your transformation has to have Jacobian 1. And what these papers are saying is, don't do this sort of thing. Don't stretch out your space. Or if you do, you better correct for it very carefully. If you hate the level of technical explanation here, you can go and read Peter Green's reversible jump paper from '95, and he gives the correct generalization of Metropolis Hastings for deterministic transformations and more complicated settings. So Green's algorithm tells you to include a Jacobian term in the acceptance ratio, and that derivative is exactly the factor of 9 that I've got here by hand waving. So that's something that you should be aware of, but you don't normally run into very often. So where we left off before our break was the Metropolis Hastings algorithm. And this algorithm is very easy to implement. We have to decide where we're going to initialize. We have to decide this distribution Q. We need to be able to evaluate pi. And we need to decide how long to run for. And that's it. We just need to be able to evaluate this function. We don't need to know all of the details. The algorithm doesn't care what your data are or what the meaning of your parameters are. You just need to be able to evaluate this function. So here's the complete code for the Metropolis method. You give it your initial condition. You give it a function handle saying, this is my target distribution, or actually the log of my target distribution for numerical reasons. How long do I want to run for? And I'm going to assume a Gaussian proposal mechanism, and so I just give it the step size, the width of that Gaussian. So the algorithm has a main loop for the iterations. The proposals are a Gaussian perturbation of your chosen step size. You evaluate how good that proposal is using the function handle that you gave it. So that's the only place that knowledge of your model enters the method. You decide to accept or reject with this probability ratio, and that's it. So it's a very short piece of code that lets you explore plausible explanations of a vast array of models. It might not scale that well to enormous data sets and enormous models. That's why it's still an active research area at NIPS, and there are several workshops on this topic. But for a lot of problems, it's a good starting point that with very little mathematics gets you answers. So here's the simplest case of running this code. So here I've created a new little function, sigma, which will create these plots. And it just calls the Metropolis code from the previous slide for a given step size. And it's going to run for 1,000 iterations. And the function handle I'm giving it is just a half x squared, or a half theta squared, minus a half theta squared, which is the log probability of a unit Gaussian, or a standard normal distribution, up to a constant. So my target distribution here for testing purposes is just a Gaussian distribution. And in this middle plot, I've drawn the graph for a step size of 1. So I initialized at 0. Instead of drawing a sample from a Gaussian independently, I sample from a Gaussian centered on where I currently am. And then I decide whether to take that move or not. If I didn't reject any moves, I'd wander off to infinity. But by rejecting about a third of the moves, this sequence over 1,000 iterations explores my space between plus or minus 1 or 2 and explores this distribution. So if I crushed this plot horizontally and drew a histogram of where the Markov chain had gone, I'd get a bell curve. I'd get my target Gaussian distribution. There was a free choice here, a step size, and I could set this step size to 100. So now I start at 0, and I make ridiculous proposals. I say, maybe try going to plus 78 or minus 48. And those places have basically 0 probability under this Gaussian. So for hundreds of iterations at a time, this chain just stays where it is. It's a valid algorithm. If I ran this for billions of iterations, it would explore the correct distribution. It just does so very, very slowly. So this step size is important. If rejecting a lot is bad, I could decrease the step size to, say, 0.1, and then I could accept more. So in this trace, I only rejected twice in the entire run. And that's terrible. That means that the method basically doesn't work. And that's possibly surprising. In rejection sampling, we don't like rejections. It's just wasted computation. We want acceptances. But in the Metropolis method, rejections are a key part of how it works. The whole point is the rejections tell you where your target distribution is. They tell you how to explore your distribution rather than wandering off to infinity or staying where you are. And this trace that we're looking at is almost exactly a Gaussian diffusion with step size 0.1. Because it's roughly experienced no rejections, it hasn't actually seen anything about our target distribution. We need to run for many more iterations before we get some sense of the support of our distribution and its relative probabilities. So we need the rejections, and you can theoretically derive what the right acceptance rate should be. So for one-dimensional proposals like these, the optimal acceptance rate turns out to be about 44.1%. And any value is valid, so you can aim for an acceptance rate of roughly a half, maybe a bit less, and the method will work well. And it will still work to some extent if you get it wrong. So you tune the step size on a preliminary run until you get the acceptance rate you want. If you're doing proposals in a large number of dimensions, then the optimal acceptance rate turns out to be 0.234, so about a quarter. And again, you would tune the step size until your acceptance rate was about a quarter. So, going to shift a little bit more into understanding how we run these things and what it means. So as a reminder, we're doing Markov Chain Monte Carlo. You, the user, tell me what model you're interested in. You write down the probability of everything, which defines a stationary distribution that will tell me what plausible parameters are. You initialize the parameters somehow to some setting that vaguely makes sense, and you run a Markov chain that then ends up exploring the space of parameters. So it will explore the slopes and intercepts of lines that intercept your data, or the weights of your neural network that give reasonable predictions on your data set. And if you run this chain for a long time, then the distribution over where you end up is the target distribution. And if you ran for one more step, the distribution over where you end up would still be your target distribution. And so what that means is we can now form estimates of integrals. So the average value of our function evaluated on one of these states from our Markov chain is going to be our integral if we run the Markov chain for long enough, if S is a large number. And we could use an adjacent sample, and the average value of this function will also be this integral, because this parameter here has come from pi. So here I've got two unbiased estimates of my integral. I could run my chain for S steps, or I could run for S plus 1 steps, and I get two different estimates. Because they're both unbiased, I can average them. I could add them up and divide by 2, and that would give me a new unbiased estimate. So I don't need to throw one of these away. Two adjacent steps on this Markov chain are going to be really close to each other. These aren't independent estimates, but they're both unbiased, and they don't need to be independent. I'm still allowed to average them, and it will still be unbiased. So in general, what we can do is we can write down the simple Monte Carlo estimator that we would write down if we had exact samples, and use it anyway, even though these samples came from a Markov chain, and they came from adjacent steps of a Markov chain. And for large time steps, we will get unbiased estimates of this integral. For small times, there's this bad thing that happened here. We had a transient phase where we're not really sampling from our distribution. So that contaminates this sum a bit, and we might not have an unbiased estimate of this integral. But in the limit of taking a large number of steps, it doesn't really matter whether we include this transient phase or not. So this expression is still a consistent way of estimating the integral, whether we discard this burn-in period, which some people do, or not. I would tend to throw away like 5% of my chain just because, but it doesn't really matter whether you do or not. All right. So then how long do we have to run this thing for? And figures like this one are really misleading because they're in 2 dimensions. And we're not really interested in doing MCMC on 2-dimensional distributions. There are better numerical methods than Markov chain Monte Carlo for 2 parameters. We're interested in high dimensions, but they're hard to draw on a slide. So here's my attempt. High-dimensional spaces are really spiky and weird. So there are all these corners of parameter space which are kind of far away from other corners of parameter space, but they might also be good explanations of our data. So this is a cartoon, and it's really a 2-dimensional distribution, but it's got isolated spikes, which is more what you're like in high dimensions. And what I've done here is I'm exploring the uniform distribution over the gray region, and I initialized here at the bottom. So I ran the metropolis method for 2,000 steps. It took some random walk around the support of this distribution. It rejected whenever it stepped into the white void. And I ended up here on this run. I'd end up somewhere different if I ran it again. So I'm going to claim that that point there is very, very nearly a sample from my target distribution, from the uniform distribution over that gray star. If I hadn't run for 2,000 steps, if I'd only run for 100, then I'd be less happy. So it took me a long time to escape from this arm down here. And what you see in the top right is the distribution over where you end up if you only run the Markov chain for 100 steps. So it's really probable you're stuck in the bottom arm of the distribution, and there's some probability you escape elsewhere, but not enough. On the other hand, if you run the Markov chain for 2,000 steps, the bottom right of the slide shows the distribution over where you end up after 2,000 steps. And to a few significant figures, it's correct. It is the distribution we aimed for. So here, 2,000 steps is long enough. I've done the maths and I've shown it. So I brute forced this numerical computation. This slide took the longest out of the whole presentation to create. And so I hope you appreciate it. It's possibly a bit surprising. So if we look at this Markov chain, it didn't wander into this arm at all, or this one, or this one, or this one. It ignored most of the state space. How can I possibly claim that that there is a fair sample when it has no idea what's going on up here because it didn't even go there? So I think this is a fair confusion. It takes a while to get in your head how these algorithms work. For this particular distribution, 2,000 steps is long enough. The distribution over where you end up is this. We didn't go up this arm this time, but if I ran it again, I could do. If I wanted 12 fair samples from my model so that I could make a reasonable prediction, I could maybe run this thing for 24,000 steps, and I could get 12 independent samples or nearly independent samples. And I could use all 24,000 steps in my average, and I'd have a lower variance estimator. So I could get really good predictions here, even though on a short run, the Markov chain doesn't explore some of the modes of the distribution. And on interesting distributions, you could easily have thousands or an exponentially huge number of modes, and your Markov chain is never going to visit the vast majority of them. And it's a mistake to think it has to. So if you had to enumerate your whole state space, why are you doing MCMC? Why don't you just do your sum by hand? So the whole point of these methods is that you can ignore most of your state space. You gather samples that are representative, and you can use those to make predictions. All right, so now we've got this technology. We've got the Metropolis Hastings algorithm, and we've got some understanding of how to use it. We just run along Markov chain and use wherever it goes as plausible settings from our model, even though they're not independent, even though it won't explore the whole model. And there's still a lot of choices about what we would do. So if you were to create an MCMC scheme, you need to make choices. Is this Q distribution going to be a local diffusion, like I've shown in all my slides so far? Or are you going to be clever and do something like approximate your model and try and propose from an approximation to your model? Are you going to update just all of your parameters, like perturb all of them? Or are you going to pick a parameter at random and move just one of them at a time? It might be easier to control the step sizes for that. Or you might be able to share a lot of computation if you only move one parameter. So for all these different choices, you get a different transition operator. And any of these transition operators are valid Markov chain methods that you could use in an algorithm. And something I really like about MCMC, Markov chain Monte Carlo, is that it composes very nicely. You don't have to come up with the best method. What you can do is have several transition operators and use all of them. So if you had 3 transition operators, A, B, and C, you could use them each in turn. So if you started out with a sample θ1, which came from your stationary distribution, you could apply a transition, and that would give you another sample which also marginally comes from pi, because this is a valid transition operator. So you can feed that into the next transition operator, and by induction, every time you take a step with any of these transition operators, you will have a valid sample from your distribution. So the concatenation of all these operators, A, then B, then C, can take a sample from your distribution and spit out another sample from your distribution, and so it leaves the distribution invariant. And together, they're a valid MCMC method if they're ergodic. If all of these operators together can get you from anywhere in your state space to anywhere else, then your proof is done. You have a valid MCMC method. So these things individually don't actually have to be ergodic. Transition operator A might only update variable number 1, and transition operator B might only update variable number 2. So transition operator B is not ergodic. It only moves variable 2 and never explores the others. But that's OK as long as together it's a valid method. So the concatenation of different methods can be better than any of the individual transitions by themselves, as long as they contribute something towards exploring the state space. The most famous example of having a series of operators like this is Gibbs sampling. Gibbs sampling says, take one of the variables from your model and resample it from its conditional distribution. So if you had a bunch of binary variables, like an image model, or binary variables like our indicator variables saying whether we had outliers or not, you take one of those variables out, forget what your current setting of it was, you look at all the other variables, and then you decide, do I want to make this variable black or white? And then you select another variable, either at random or in turn, it doesn't matter, and you make the same decision again, you resample it. So because we can always sample from discrete distributions, Gibbs sampling is very easy to implement for discrete variables. Here I just need to sample from a one-dimensional binary random variable, and I know how to do that. Continuous variables are a bit more tricky. Here I only move horizontally or vertically. I update one of my 2 continuous parameters at a time, or in general, one of my several at a time. And given a current location, you need to work out what the conditional distribution of the variable you're updating is. So if that conditional distribution happens to be something with a name, a gamma distribution, a Gaussian, you can use library routines to sample from it. Or you might have to prove something about it, like it's log concave, and then you can use clever adaptive rejection samplers that know how to sample from those conditionals. So Gibbs sampling can involve doing some maths and being clever, although there is software that does that, encodes some of that cleverness for you. So one of the most successful pieces of statistical software is Bugs or WinBugs, and its successors like JAGS, and now in this community we have Stan and other software. And what Bugs and JAGS does is derives these conditionals for you for your model and works out how to do all of the updates. And then you don't have to set step sizes, and it explores your whole model. If there's a variable it doesn't know how to update, it can fall back to doing a metropolis method and update that variable that way. So when you implement Gibbs sampling, it might not work very well. This red distribution is correlated. If we know θ1 is high, then θ2 is probably high as well. And that means that these horizontal and vertical moves can't be very long compared to the distance that the Markov chain has to traverse to explore the whole distribution. And that will get worse if the variables are more correlated. So there are a bunch of things we could try and do about that. One is we could try and transform the space to make the variables more independent. We have to be slightly careful about how we do that. There's a method called adaptive direction sampling where there are delta functions, and you have to be careful about what they are and include a Jacobian term. Another clever thing we can do is blocking, which is updating more than one variable at once. So to give you an example of that, I'm going to have to talk about a particular model, and I've made this as simple as possible. So here we've got 2 unknowns, regression weights and binary variables saying, are we an outlier or not? We have a Gaussian prior on our regression weights. We think 10% of our data points are going to be outliers, And our labels are either noisy versions of a straight line, or they're junk if the binary indicator is 1. So this is an example of a model where lots of it is quite simple, tractable stuff we know how to deal with. We're really good at doing computations with Gaussian distributions and linear combinations of Gaussian distributions. So for this model, we can derive exactly a Gaussian distribution on the weights if we temporarily pretend we know which data points are outliers. So if we pretend that we know which data points are outliers, we can ignore them, and then we just have a linear regression problem. And then we know exactly what this posterior distribution is. So it turns out you can have one line of vectorized code in MATLAB or NumPy or whatever that will sample all of these weights at once. They might be strongly correlated, but we can just replace them all. And then we can have another line of possibly nice vectorized code that will update all of the indicator variables, temporarily pretending we know what the weights are. So there's this nice block Gibbs sampling scheme, which is a for loop containing 2 lines of code that just updates W and then updates Z alternately. Very easy to implement and might work quite well. So that's a clever trick we can do. The unfortunate thing here is that there's lots of clever things we could do, and we don't know which ones to do. So here's another clever thing we can do. When we know the whole distribution over the weights, that's a sign that we probably know how to analytically integrate them out of the model as well. If we're able to form and normalize this distribution, we know how to do integrals involving W. And indeed, here we can analytically work out up to a constant the posterior distribution over the indicator variables given the data by integrating out the weights. So you can evaluate this probability up to a constant for any setting of what's an outlier and what's not. Because if we say these are the outliers, you ignore them, and then you have a tractable linear regression problem. So you can run MCMC on a collapsed problem where you don't have to talk about the weights at all. You just update what you believe is an outlier. And you could do that by Gibbs sampling. The Zs would no longer be independent, so we wouldn't be able to vectorize this. We'd have to sequentially go through the Zs. But we don't have any real numbers, and we just update these things, and it's easy. We can also collapse out the Zs and update only the weights, maybe using a fancy method like Hamiltonian Monte Carlo, and we then don't have to deal with the discrete variables at all. And this is kind of annoying because it's not at all obvious which of these 3 ideas is the best one. And it will depend on stuff. So it depends on, are you going to implement this on a GPU and you really care about vectorizing? It might depend on the structure of the model and the data you have. So maybe it's really obvious what all the Zs are for your data, and then exploring the Zs is just go to the setting which is obviously correct, and then you're done. You have an analytic answer. So this method might work really well, but it depends. And in most of the probabilistic models that appear in NIPS papers, the models are a lot more complicated than the one on this slide, and there's a bunch of choices about what you can collapse out of the model. So you'll see papers on things like latent Dirichlet allocation or topic modeling, where there are different parts of the model that you can collapse out, and there'll be different trade-offs on which one you should do. And this isn't just an issue with Monte Carlo methods. If you're doing variational inference for these models, you can also collapse out different parts of the model. So one of the great challenges for people doing probabilistic programming is that they're claiming you can define your model, and a clever compiler will work out how to do inference for you, which means including deciding what choices to make here. And these are choices I don't know how to make half the time. So it's a really ambitious research agenda that these people are attacking, and there's a lot of theoretical problems there. This slide has this idea that sometimes we can do analytic math, so we can integrate out analytically some of the unknowns in our model, and then sometimes that makes things better. But sometimes it's good not to integrate things out because we might get convenient updates that work well. And we can take that idea to an extreme and actually introduce extra variables just for our own computational convenience. So there's a whole family of Markov chain Monte Carlo methods called auxiliary variable methods that do the reverse of being clever and integrating things out and put in extra variables that we didn't need to. So we form a new target distribution over the unknowns that we're interested in that actually appear in our, appear in our model, and some extra variables I'm calling h, which might have nothing to do with our problem at all. We just put them in for the fun of it. And we need this target distribution to be consistent with the distribution we're interested in. And then we can sample a Markov chain that explores both theta, our unknowns, and the auxiliary variables h. We then marginalize by throwing all the h's away, and then we're left with samples from our unknowns. And most work in MCMC can be interpreted as coming up with a clever representation of your problem, which might involve some auxiliary variables, and then running Metropolis Hastings on it. There are a few methods that aren't Metropolis Hastings, but most of them are basically Metropolis Hastings. So you know most of what you need to know. It's then just down to the details of how you're going to be clever. So the first auxiliary variable method was called the Swenson-Wang algorithm. I've already mentioned Hamiltonian Monte Carlo is very popular in this community. At the moment, there's a large amount of work on so-called pseudo-marginal methods. These are methods where you can't actually evaluate pi star even. You can't evaluate your target distribution up to a constant, but you can estimate it. And pseudo-marginal methods are just clever auxiliary variable methods where the auxiliary variables you introduce allow you to use estimates of your distribution rather than exact computations. So the auxiliary variable method I'm going to quickly tell you about is called slice sampling, because it's sort of a beautiful, simple method, and it's one that I think is a really good entry into running MCMC if this is something you want to try out yourself. So this is a method by Radford Neal, and the idea goes back to rejection sampling. So I'm going to show you a one-dimensional figure because I'm going to assume we're just going to update one parameter at a time. And in rejection sampling, we need to sample uniformly underneath the curve, right? And that can be hard to do. But we're doing Markov chain Monte Carlo. We don't actually need exact samples. We just need to take a Markov chain, a random walk. So what slice sampling does is says, instead of sampling exactly under this curve, I'm going to take a random walk underneath this curve and see where I end up. So to talk about being somewhere underneath this curve, I need to introduce a new variable, h, which is the height. Where am I between 0 and the height of the curve, which is pi star? So given this distribution over two variables, theta and h, my target distribution is just uniform in this area under the curve, and I can do Gibbs sampling. I can update one variable at a time. So I could update the height, given where I currently am. So I'm going to move vertically, and I just sample from a uniform distribution on that line. So that's easy. And then I can turn my attention to the parameters, and I need to update myself along this horizontal gray set of segments. And that set of segments is called the slice. So slice sampling boils down to how do I move around the slice. For unimodal distributions, this is really easy to implement. You can do rejection sampling, but the rejection sampler is really simple. I want to sample from this segment underneath the curve. I just write down a bigger segment than I need, so I just push out a bracket until it's clearly outside the distribution, which is easy to check. Then I try sampling on that interval. And in this case, the sample is not on the slice, so I'll need to try again. But I can be clever. I now know this whole region over here isn't acceptable, so I can shrink in my bracket. So the algorithm very rapidly, exponentially quickly, makes the red interval tight, and at some point I will definitely get a sample somewhere on the slice. So these rejections are just part of the internal working of how I'm going to move horizontally. They're not part of my Markov chain. So this is a method that will keep looking until it finds an acceptable point, and then it just goes there. Unlike Metropolis Hastings, I don't need to record rejections. I don't have horizontal lines on these trace plots. And what's good about this procedure is that I don't need to know in advance how broad this distribution is. It automatically shrinks in to find a sensible step size. So I don't need to tune things as much as for Metropolis Hastings. If the distribution's not unimodal, you have to be a bit more careful. So Radford-Neal's paper had a series of updates that tells you how to move around on the slice. And we give up on Gibbs sampling. So given that we're currently here, it might be that we never transition over to this part of the slice. We just move somewhere within the local region. And that's OK, because all we need to do is leave this conditional distribution invariant. We don't actually need to sample from it exactly. We're running a Markov chain. And the Markov chain will be ergodic if it's possible to go down, along, and up, and eventually explore the whole area under the curve. So really, you'd want to look at the paper to get the details right, because it's very easy to get the details slightly wrong on this algorithm. But it's very easy to implement. You slap down some initial interval. You extend it until it sticks out of the curve, and then you just sample from it, as I showed you on the previous slide. So these algorithms are really easy to use because, unlike Gibbs sampling, you don't need to derive a load of mathematics. You just need to be able to evaluate your target distribution, which is the probability of everything. It doesn't have these rejections, so it doesn't have these long horizontal regions in a trace plot, and it adapts to step sizes. So as a first method to run, it's often the one to try. If you're wanting to parallelize things or really get the fastest performance, you might want to tune a clever Metropolis-Hastings method. But if you've got a simple problem and you want to try out MCMC methods for the first time, this is what to do. Radford-Neal's paper, which I've linked to here, and the slides will be available, is a great read. It has a lot more ideas than I've explained here. With co-authors, I have a paper, Elliptical Slice Sampling, which is a multivariate version of slice sampling that's good for Gaussian processes. And we have a paper on arXiv called Pseudo-Marginal Slice Sampling. This tells you how to use this black box, simple updates, where you don't even know how to evaluate pi. You can just estimate it randomly. So these algorithms are really broadly applicable. OK. So what I'm going to do for the sort of final 10, 15 minutes or so before questions is tell you a bit about the sort of practical issues of like actually running these things and getting them to work. And I think I know what a lot of you will be thinking, because I've given a few of these tutorials, and the main questions I get are things like, how long do I need to run this thing for, and how do I diagnose if it's correct? And if you look at papers that use MCMC methods, you'll see that they're full of these sorts of diagnostics. So here are some figures I've stolen from a NIPS paper. And one of the things you might do is plot a trace plot. This was run for 5,000 iterations. And some quantity, some unknown theta is plotted over time. There's a burn-in period. So maybe when you're estimating things, you want to throw away the first 1,000 steps. Hopefully, this thing has reached some sort of equilibrium. But eyeballing that, I'd probably run it for at least another 10 times longer and see what happened. It's now 15 years later, so that would be easy to do. Another thing that a lot of papers do is plot autocorrelations or autocovariances. So how correlated is my state theta at time 0 compared to 400 time steps later? And if any of your variables are sort of quite predictable or correlated, if you know where they were 400 steps ago, then you know that 400 steps isn't long enough to like get an effectively independent sample. So if you have high autocovariances, it's bad news. If the autocovariances all appear small, it doesn't mean you're OK, but you know that you're in trouble if you get large autocovariances. So the standard software like RCoder that will create these plots and run a whole bunch of other diagnostics for you. And I've linked here a really nice review on some of the practical issues of running Monte Carlo. But actually, none of this stuff is, I think, the thing you should worry about first. The thing that I worry about first is that when I've implemented a method, it's probably wrong. I've probably just screwed up my code, right? And there's this really nice paper by John Gawecki where the title of the paper is Getting It Right. We all want to get things right. And the thesis of this paper is that your MCMC code becomes big and complicated. You've probably messed up somewhere. And then there's no point running a load of diagnostics if you're busily exploring the wrong distribution. So what we'd like is some way of unit testing our code. And these are randomized algorithms, so they can be a bit hard to test. So he had a neat idea. It's related to other checks that other authors have done, which was to implement code that can draw samples of data from your model. So we spent ages writing MCMC code that will explore plausible parameters. It would be really easy to write code that would generate synthetic data. I recommend you do that anyway, just to eyeball what your model thinks. So if you have these two pieces of code, you can check that they're consistent with each other. And as this second piece of code is fairly easy to write, if there's a mistake, it's probably in your MCMC method. So here's how you do it. Here's how you get it right. You generate some synthetic data. So make up some parameters, generate some data, and you know what parameters generated those data. You can use your Markov chain code to move to some other parameters that could just as easily have generated that data if you didn't know otherwise. So you move the parameters. You then throw your data set away and generate a new synthetic data set from scratch, a new data set that could also come from those parameters. So you've moved the data set. You then clamp the data set and move the parameters. And you go back and forth. So what we're doing is we're running a Markov chain on the joint space of unknowns and data, exploring every possible setting that we think our model thinks is reasonable before we see any real data. And if that code is consistent, we'll do that correctly. And the parameters will explore their prior distribution. So if you had some parameter like a regression coefficient, which had a Gaussian prior, you could plot a histogram of that parameter, and it should look like a Gaussian. And that doesn't happen when you've messed up your code. If you introduce artificially a small mistake into MCMC code, what normally happens is some whole region of the state space becomes disfavored, and you get a chunk cut out of your histogram. So you plot this histogram, it should have been a bell curve, it's obviously not, you know something's wrong. And this isn't like a hypothetical story. John Goecki admits in this paper that he went back and checked his previous papers and found mistakes in his published results. Embarrassing. Fortunately, I read this paper after that, and I submitted a paper to NIPS 2010 where I know that in the day of the submission deadline, I made some change to my code. I ran this check and went, phew, realized I'd made a mistake and fixed it up. So, this check meant that either my paper wasn't rejected or I didn't have to embarrassingly correct it later. There's plenty of other papers where I've had to do embarrassing corrections later, but this wasn't one of them because it was this useful tool. There are a bunch of other consistency checks that are useful. So I started out by saying there's not much point being very carefully Bayesian if our model is overly simple or wrong. If you read Gelman et al.'s Bayesian data analysis book, there's a section on posterior model checking that says you can use the samples from your posterior not just to check your code is correct, but also to sanity check whether your model makes any sense. And that's sort of a really valuable toolkit that comes easily with MCMC methods. You will be creative, and for your problem, there's all sorts of things you could do. Like, if I draw synthetic data, what sort of predictions do I make compared to if I knew the truth underlying the data? If I can't make good predictions in a synthetic world, then I know my system isn't going to work well in the real world, and I should go back to the drawing board. So that's something in the way of practical techniques. What should you actually do? Which method should you use? So if you're running forward simulations, you're generating from particular distributions to simulate something, then you need exact samples. Markov chain doesn't really cut it, so you're going to use something like rejection sampling to draw from the distribution you want to. But if you have a complicated distribution, like from a Bayesian posterior, rejection sampling won't work. So you're going to use importance sampling if you can get away with it, which is almost never, but on small, noisy problems. And for more interesting problems, I suggest that you start with MCMC methods. And if your values are real value, if your variables are real valued, I'd suggest starting with slice sampling. If you're careful and you know what you're doing, you might get Metropolis Hastings to work better. And if you're clever about deriving your updates, you could do Gibbs sampling or one of these other methods. So I'm going to point you to some reading. These two reviews are what I learned Markov chain Monte Carlo methods from. So David Mackay's textbook is excellent. Radford Neal wrote this literature review as his transfer document to becoming a PhD student. It's about 130 pages, and it's amazing. I learn something new every time I read that document. There's a new review of Monte Carlo methods in this very expensive book by CRC, but there are several free chapters online that cover things like the maths behind the green method, so if you're doing clever deterministic updates, getting that right, describes Hamiltonian Monte Carlo, and also a bunch of stuff to do with diagnostics and checking. If you want to go beyond this introductory seminar at NIPS, there are a lot of relevant workshops. So I'm probably missing some out, but the ones here all have a very large Monte Carlo method content. So these methods are of interest to real problems at NIPS. The first two are sort of, how do you run these things when your models are a lot bigger, when getting a Markov chain to mix is going to be hard, or computing with a large data set is hard. Black box learning is about, well, how do I make all these free choices? Like, how would I represent my model when I don't want to have an expert at hand? And Bayesian nonparametrics is one of the biggest uses of MCMC methods. There are also a couple of workshops that I put at the bottom where they think Monte Carlo methods are a terrible idea, and they've got much better solutions. So go to those workshops too. They have ways of solving inference problems that don't use these noisy random numbers and get more accurate answers. But even if you were going to use the methods from these workshops, what would you check them with? I'd check them with MCMC. And there's still a lot of problems. Bayesian statistics is dominated by MCMC methods, not yet the methods from these communities. So that's the challenge to them. And I hope they succeed to replace MCMC methods. So what I'm going to do, just to finish with, is show you an example of MCMC running before I have some questions. So 3 years ago, there was a Kaggle competition to do with predicting locations of dark matter in the sky. And unlike some Kaggle competitions, this didn't have an enormous data set, and it didn't have a really complicated model. But it required doing the statistics kind of correctly. So the top 3 entries to this competition were all basically statisticians who knew how to do statistics correctly. And the top 2 winning entries both used MCMC approaches. So one of those approaches used slice sampling. And here's an example of an easy data point from that challenge. So this is a synthetic image showing you the locations of galaxies in a patch of sky, and lines showing the orientation of those galaxies. So most galaxies appear to be elliptical disks, and they point in some direction. And naturally, they would have a uniform distribution over how they're oriented. And you might be able to spot, and it's not very hard to see in this figure, there's a suspicious region where the orientations don't look random. And that's caused by a lensing effect. There's dark matter between us and the galaxies, which are bending the light and causing this distortion. So what you can do is solve the inference problem. Where is that dark matter, and what are its properties? So we have theta, our unknowns, are the x, y positions of this dark matter halo, its mass, its size, and its shape. So you might have 5 or 6 parameters describing the dark matter. And then you can run a Markov chain in that 6-dimensional space. So what I'm showing here is just the walk the Markov chain did on 2 of those parameters showing the position. So I initialized a dark matter halo at a random location here. It used slice sampling, so it adaptively saw that it could take a massive step and then some bigger steps, and then it took a load of really tiny steps. I didn't have to tune these step sizes because it did that for itself, and saw that it knew the dark matter location was around this true location with high precision. So this was really easy to implement, like literally a few minutes once you know what the model should be, but this is an example of a problem where you probably shouldn't do MCMC. So here, if I ran an optimizer, I could just say that that is the optimal location. I could measure a curvature or something else to come up with a Gaussian approximation, and I could put error bars on that answer. So this is an easy inference problem. It's not that high dimensional, and MCMC is just not worth the hassle. A lot of the data sets were a bit more complicated, though. So here's a more representative patch of sky from this challenge. And we were told there are 3 dark matter halos in this patch of sky somewhere. And you can try and spot where they are, but it's not particularly obvious. So what we can do is we can initialize a Markov chain where we explore this larger state space of maybe 15, 20 numbers saying, what are the parameters of these 3 dark matter halos? The black crosses show the right answer, and then a Markov chain can explore the positions of 3 dark matter halos. And those 3 dark matter halos move around a lot because it's incredibly uncertain where they are. After a long time, you can look at all the places they visited. The colors here aren't particularly meaningful because the halos can swap over. So I'm going to remove the color, and the intensity here is showing the mass of the dark matter halo. So it was exploring the position and the mass and a whole bunch of other stuff I'm not visualizing. And here you can tell that, yeah, we're really sure there's a massive dark matter concentration around here and around here, which is correct. We're not sure there's one here because if there is one there, it's not very massive. And there are all sorts of other places where there could be dark matter halos. So the posterior distribution here is really complicated, and I'm just showing some of it here that I can visualize. And if you fit this, and then try and make conclusions about physical theories, how does dark matter interact with gas, you just come up with spurious results, which are due to errors in your fitting. What you need to do is propagate all of this uncertainty through and use it to compute what does this patch of sky tell me about physics so that I can combine it correctly with the inferences I'm running on several million other patches of sky, which the MCMC is running on separate machines. So this was a challenge where the MCMC was very easy to implement, and really the only way I know of getting sensible predictions about the physics. So I will stop there and take questions. Thank you very much.
Please come up to the microphones to ask questions. There's microphones on the aisles. There used to be.
Is that working? Is that working? Yeah. First of all, great talk. Thank you. And thanks for the red mitten. That really made it for me.
Oh, thank you.
So the high dimensional space you talked about, you're doing this walk, and you say the corners are all heavily separated, and you had that visualization. You say you jump to another corner, if you like, and you can say that that's enough steps to get there. And I guess my question is, how do you assess whether that was a lucky early number or an abnormally long number? How many of these long iterations do you have to do to be sure that that's kind of the right number?
Right. Okay, so there's a question here that I have brute forced this problem. So I did a massive numerical computation here, which means that I know that 2000 is long enough. And that's the short answer to the question is I brute force this and then I know. But for another problem, the real question is, well, how would I know for a real model rate? So if this arm had some massive blob attached to it, and that's where the distribution really is, then 2,000 steps wouldn't be long enough because I'd need enough steps to make sure that I would explore down that arm, find where the real action is, and spend time there. So for any real model, well, not any real model, but for most real models, it's really hard to know that that isn't going to happen. Maybe if you run it for longer, you'll discover that you just had pseudo-convergence and you're actually going to spend the rest of time somewhere else. And I don't think it's unfair to say that the majority of NIPS papers over the years that have used MCMC are probably not running for long enough. They are almost certainly trapped in some small part of the distribution. And if you could run them until the age of the universe, you'd discover that they did something slightly different.
So no easy fix, basically. You just
I don't think there is an easy fix. So there was a lot of excitement in the 90s about a method called perfect simulation. So for some very high dimensional distributions like Ising models with 1 million spins. Amazingly, it's possible to prove that how many steps you need to run for. And people like Jeff Rosenthal in Toronto have some great theory for some realistic statistical models saying how long you need to run for. But most of the Bayesian non-parametric models used here, no, I don't think we're there yet.
I guess I have a quick question. But you might imagine that you might not have to mix thoroughly in different applications. So in some applications, you might just do sort of partial mixing. But if you're computing some sort of expectation, that might be reliably estimated well before the mixing is complete. Do you have any comments on that?
Yep, so great. I entirely agree. Sometimes you might not care too much about mixing. Sometimes MCMC methods in this community are used within the inner loop of an optimizer. And the sort of stochastic approximation theory that says that maybe your optimization will run out correctly even if you don't equilibrate at each step. Sometimes you're doing this thing basically as a really good heuristic for approaching the right thing, but you care about engineering performance. So there's a lot of recent NIPS papers on large-scale MCMC that haven't tried to look for convergence, but have compared themselves to non-Bayesian things by looking at test error. So in terms of engineering performance, the question might be, if I'm running for a certain amount of compute time, what's the method that will give me the lowest test error? And if that method is some MCMC that might not quite be reaching equilibrium, then great, I'll do that. If, on the other hand, I'm doing MCMC for scientific data analysis, and I'm trying to say what we believe about physics after a $300 million experiment, then I might care a bit more about whether this is the correct computation or whether it's some hack that might kind of sort of roughly be right. So I think context is everything here. And I think there's space for people playing fast and loose and trying massive systems, and there's also space for people really trying to get the right answer when you've got 7 parameters. And I think both areas are important.
Okay, if there's no more questions, I'll actually ask one then. I remember reading Radford Neal's thesis a while back, and of course being very in love with the idea of using MCMC to do inference with neural networks. And I wanted to ask you, like, I know that Radford and his students have won some competitions a couple of years ago.
2004.
2004, right? Yeah. But I don't see that much activity with Bayesian treatment of neural networks and in particular MCMC. Do you think that this is just something that will sort of come back, or do you have any perspectives? And of course, any inevitable connection to deep learning would be sort of pretty interesting.
Okay, so the question is why, when Radford Neal wrote this amazing code, FBM, that he released in about 1994, and you can still download it. It compiles, it works very well, and he won competitions at NIPS workshops in 2004 by just dusting out that code and running it. Why is it that there hasn't been so much activity since? And I think part of that is that that code doesn't really scale to enormous data sets. So they're batch methods where for every MCMC update, you need to chew through your entire data set before you make a single move. And to have these really valid Markov chain methods that statisticians have traditionally tried to construct, you kind of have to do that. And so for the NIPS community, that wasn't so interesting. It's not true to say that there isn't lots of interest in Bayesian neural nets, though. In the last 2 or 3 years, there's been a lot of work. So starting with Welling and Tay's work and a series of papers following from there, there have been mini-batch versions of Hamiltonian Monte Carlo. And to be honest, the theory is a little shaky, but empirically, these things work very well, and these methods are getting on firmer ground over time, so that's an interesting area. There's also been an explosion in interest in stochastic variational methods. So some people are using neural nets using variational approximations rather than Monte Carlo approximations. So that work is interesting. And then the Cambridge engineering group, Zubin Garamani and his student Gal and others have interpretations of dropout as doing variational approximations. So I think there's still very much interest in regularizing large systems sometimes using random sampling. It's just that it might be we need to move away from some of these traditional statistics algorithms to slightly updated versions.
All right, well, thank you, Ian, for a really, really great introductory tutorial.
Thank you.
Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.